Hello again, this is Claire, and I'd like to talk to you about the numbers we've just been experimenting with, 3, 4 and 5. Now we know they fit into the Pythagorean theorem. We've found out that 3 squared plus 4 squared equals 5 squared. So 9 plus 16 equals 25. We've found that out. So let's explore this a little bit further. What about if I multiplied each of these by 2? So increase them by a factor of 2. So that would be 3 times 2 is 6, 4 times 2 is 8, and 5 times 2 is 10. Would they still fit into the Pythagorean theorem? Is 6 squared plus 8 squared going to equal 10 squared? And would I still be able to construct a triangle that would be a right-angled triangle with 6 centimetres, 8 centimetres and 10 centimetres? So let's just test that out. So let's square 6. So we'll write 6 squared and we'll add that to 8 squared and we'll see if that in fact equals 10 squared. So we're required to prove RTP that 6 squared plus 8 squared equals 10 squared. So 6 squared is 36. And can you remember what 8 squared is? It's 64. And let's add these together. So 6 and 4 is 10. Put down the 0 and carry the 1. 3 and 6 is 9, plus 1 is 10, so we write down 10. So we've got 100. So 36 and 64 added to 100, and 10 squared is in fact 100. So let's just test that on our calculator. So it's important to use a calculator and know how the buttons work. So let's just turn it on and we'll just clear it. So we've cleared all the numbers off. So let's look at 6 squared. So we select 6 and there's a little button here which says x squared. And that is a little bit of algebra. So it's x raised to the power 2. So we select that button to square it and select enter and you get 36. So that's verified that. I'll just put the camera down a little so that you can really see that calculator. And let's try 8 squared and enter and you get 64. And let's add these together. So you can simply go 36 plus 64 equals 100 and that's verified it. Okay. But there's another way we could verify it. We could actually find the square root of 100. And that involves another bit of knowledge. So let's have a look at finding the square root of 100. So the square root symbol starts off as a tick and then has a little hat, a little roof, and that's called the radical sign. So we put the 100 underneath that. And what it means is, basically, what number multiplied by itself gives 100 underneath that little symbol. So it's a bit of a mouthful, so it's much easier writing the square root symbol. Now the square root symbol is found on your calculator too, and it's just above the x squared symbol. Can you see it? It's in black there. And it requires you to use the second function key. So there's lots of math symbols, so we have, all the keys have a second function. So you push second function and then select this x squared and that will bring up the square root. Can you see that square root symbol and the cursor's flashing? So you can just enter 100 in there and push enter and you get 10. So the square root of 100 is 10. Now we'll be using that square root function quite a bit in our studies of Pythagoras. So what about if we consider another set of numbers. What about if I multiplied 3, 4 and 5 by the factor 3? So that would give us 9. 3 times 3 is 9. 3 times 4 is 12. And 3 times 5 is 15. Do they also fit inside the Pythagorean theorem? So let's have a look at that. Okay, so 9 squared plus 12 squared, does that equal 15 squared? Well, that's what we're required to prove. So 9 squared, what's that? It's 81. And what's 12 squared? It's 144. So we could add those together. So 1 and 4 is 5. And 8 and 4 is 12. Carry the 1. And 1 plus 1 is 2. So 225 is the square root of 225, in fact 15. So let's test it. Get our calculator back again and choose second function and the square button, and now we have the square root symbol again, the little tick and the little roof, and we put in 225 and enter, you get 15. So it is indeed true that that the square root of 225 is 15 and that 15 squared is 225. So we've proved that a couple of times, and these are actually multiples of 3, 4, 5, and it's true to say that all the multiples of 3, 4, 5 will fit into the Pythagorean theorem, and they will all form right-angled triangles. So if we quickly do that, we could check the 6, 8 and 10 by selecting 8 centimetres, just making sure you can see it. 8 centimetres here, 6 centimetres in height, using the grid book to form a right angle in the corner, just here. And if we have 10 centimetres between them, and we have, you know, they form a right angled triangle. And just in here, you would be able to put the 4 and the 3, 1, 2, 3, and you would have the 3, 4, 5 triangle. And as you can see, they are very similar triangles. This one, they are in the same scale ratio to each other. And the next one I did was 12 on the base, just here, and 9 in height. So I'll just put that 9 up here. And you can see, if I join that, I would get exactly 15, which is the length of the hypotenuse. And they are similar triangles because all of the side lengths are in the same scale ratio, and you can see they're the same shape, so they're similar triangles. And we can write this as B for base, A for altitude, H for hypotenuse, and we can express this relationship very easily using some algebra, a little simple rule, which says A squared plus B squared equals H squared. The square of the two shorter sides, when added together, give you the square of the longest side, the hypotenuse. And that's the Pythagorean theorem. Some people write it A squared plus B squared equals C squared. But it's the same thing. I like to use H because I like you to remember that that hypotenuse is a very special side length. Okay, thanks for your attention, and I'll see you in the next tutorial. Bye.